Hello everyone, today we're talking about echelon forms. This is material from 1.2. So I want to talk about give you some definitions of terms I've been using in previous lectures, kind of give you all the details here. So let me recall the setting here. Suppose M is an M by N matrix. And remember our conventions here. M is the number of rows. N is the number of columns. Okay, so first notion I want to define is what's called a leading entry of a row. So it's leading entry of a row in M is the leftmost non-zero entry. So, you have your matrix here. Maybe I'm looking at the second row. I might have a few zeros here, and then at some point I have a non-zero entry. That's what I mean by the leading entry. Okay, so with that definition, I can tell you what an echelon form is. So a matrix M is in, well, I usually say row echelon. I'm just going to say echelon form. It's the only echelon form we're going to talk about. So if three things happen, so the first one is that if you have any row of all zeros, this should be at the bottom. So you might have some rows that's just all zeros, and you can put those to the bottom basically because we don't want to think about them. Second condition, maybe the most important one, is that each leading entry of a row, so this first non-zero term, is in a column to the right of a leading entry of a row above it. Okay, and so I think of this as kind of the staircase property or staircase shape. Okay, so what I mean by that is, if you have your matrix here, so maybe you have, in the first row, you got your leading entry, let's say, is there. I don't know, ... what it looks like. In the next row, when I get the next leading entry, it has to be to the right of where I was before. So you can't have a leading entry that's below or to the left. It's got to be to the right of where you were. And, you have to take at least one step to the right. If you think of these leading entries as steps, I took it, in this case, 2 steps. But you have to take at least one. So maybe for the next one, you took 1 step. And so if you think about this as, like I said, if these are steps in a staircase, then this gives you this kind of shape. Okay? And number 3 is kind of a little bit redundant maybe, but just to drive this idea home, we want to say that all entries in a column below a leading entry are 0. Okay, and so if I look at any of these leading entries, I have to have zeros below. So this is, here's the leading entry, and everything below it is 0. This should remind you of previous lectures where we were clearing below these, these terms that we decided to eliminate. So a piece of terminology that we've been using already is that the positions of leading entries of a matrix in echelon form are called the pivots. Okay, so the pivots are, I'll circle them here, right? These are I say position because, the fact that it's 4 is actually not so important to me, but I want to know that it's in the first row, second column, right? And this is in the, say, second row, fourth column. And I'll also talk about pivot columns. So if you only want to know where which column it's in, that's also going to be important. So for instance, this did not have a pivot in the first column or the third. There was a pivot in the second and I guess fourth, fifth. Okay. Okay, so let me just now say, so that's the notion of an echelon form. Now there's something stronger we could ask for. So M is said to be in what's called reduced echelon form if, in addition, two things are satisfied. So the first thing, so again, we want to know that all of these things above were satisfied. So we still have these three things, but now we're going to ask for more. So the first thing we're going to ask for is that not only are those, well, so the leading entries we know can be anything when we were in echelon form, right? So these leading entries can be any number. What we want to know in reduced echelon form is that the leading entries all have value 1. So if you want to think about, using your row operations, you would scale your row to get them to equal to 1. And the next thing we want to know is that not only do we have that staircase property from above where all, everything below a leading entry is 0, but we actually want to have entries above the pivots to be 0 as well. So each leading entry is the only non-zero entry in its column. And so, what I think about is that you've cleared below and above each pivot. Okay, and so in a picture here, well, so I've maybe I'm looking at this row and I've got a pivot here. I know it's got to be 1, right? Not only do I have zeros below it, but there's actually zeros also above it. Okay, and so that's this extra condition for the reduced echelon. Okay, so I'm going to do an example in a second, but maybe just a fact for now is that, we've seen this already before, but maybe say number 1 is we use row operations left to right, top to bottom to obtain echelon form. And here we can determine if the system is consistent. So remember we saw that last time that we're consistent as long as we don't have that row of zeros with something non-zero at the end. And in fact, we can tell how many solutions exist. So echelon form is enough to kind of answer those first two questions we've been talking about. And maybe fact 2 is that we use row operations now right to left, bottom to top to obtain the reduced echelon form. Reduced echelon form. And here, this is used to describe the solution set. And we'll say more about that next time, but I want to do this, so this will be the topic of the next lecture. But I wanted to end this lecture with just an example that I'm taking from the book here. So let's see, so let me pull up my printout here. So I just want to do a quick example where I kind of go through all these. I don't want to have to write them all, the matrices out every time, so I'm going to cheat and take this from your textbook. And so, I'm going to go through this relatively fast. If you want to slow down, this is from your text. But here's the idea, right? So here's a matrix I've given you. It's a 3 by 1, 2, 3, 4, 5. I should point out that the book doesn't always put in that dashed line. I think maybe just to put it in to emphasize that this is the right-hand side of an equation, right? There's 0x1 plus 3x2 minus 6x3 plus 6x4 plus 4x5 equals minus 5. Okay, so anyway, here's the matrix. I want to put it in first echelon form and then reduced echelon form, okay? So here it says, step 1, start with the leftmost non-zero column, which is the first column. This is a pivot column, but notice that I don't have a pivot to work with here. This is the leading entry in the first row is 3. So what I have to do is swap row 1 with either row 2 or row 3 so that I have a pivot with which I can clear. So they've decided to swap, let's see, so going down to here, this is the pivot column. They're going to swap, it looks like, row 1 and row 3. So we're going to swap row 1 and row 3. And what we get is, or he calls it interchange row 1 and row 3, I get to this new system. And now I have a pivot that I can work with in the first row, first column. And I'm now going to clear below everything, right, below that pivot. So in the second row, I've got a 3. So I'm going to use that first row to clear. I'm going to replace row 2 with -1 times row 1 added to row 2. Okay, and so that's what they're going to do here. So using row 1, I replace row 2 with, like I said, -1 times row 1 plus row 2, and that clears that entry, right? So for instance, I took -1 times -9 is 9, plus -7, that gives you a 2. That's why there's a 2 there. And you do that for every entry, and you get this new row 2. Okay, so now you keep going. You say, now go to the next row. What you see now is that there's a non-zero entry here. That's going to be my next pivot. Okay, so yeah, indeed, they're explaining things here. I'll let you kind of read that. But my next pivot is here, and so I'm going to clear below it by, again, taking a multiple of row 2 and adding it to row 3, replace row 3 with what I get. So he's taking -3/2 times row 2, adding it to row 3, and what I get is this, right? So for instance, if I take -3/2 times 4, what is that? That's 6, and when I add it to -6, I get 0. And it turns out there's another 0 here, etc. I do that for the whole thing. And I get this new matrix here. Now this new matrix, well, we continue, right? So we go left to right, and we say the next pivot position would be this guy here. Now we're done because there's nothing to clear below. There's no information below that pivot. So at this point, so here we go. He's now circled the pivot. So the pivots are going to be these 3 positions here. You've got that nice staircase position. This is now in echelon form. Okay, so as I said, they've reached echelon form here. What they can tell is that at this point, right, so I want to emphasize that at this point, I can tell that this system has a solution, and in fact, it has an infinite number of solutions because I have what are going to be called 2 free variables. We'll do an example of this in the next lecture. So this is a consistent system, and it has 2 free variables, so this implies an infinitely many solutions. Okay. Now I'm going to keep going with the row operations to show you what reduced echelon form it looks like. But again, if this is all I want to know, if I want to know the consistency of the system, I could stop here. But let's keep going. So the idea with reduced echelon, okay, so we're in echelon form here. Let me just emphasize. If I want to do reduced echelon, like I said, what I do now is I move right to left, bottom to top. So I start with the pivot here, and I clear everything above, right? So this is going to be my next step. So how do you clear above? Well, same deal as before, just kind of working backward in some sense. So if I want to take that 2 away, I'm going to take -2 times this row 3 and add it to row 2. So I get, the 0 here, and this would become what? -2 times 4 is -8, plus -6 is -14. So that's what I'm seeing here. And I did the same thing with the 6. So he also, in one move, he took -6 times this 1 and add it to here. If you take -6 times 4, that's -24, plus 15 is that -9. But so he's cleared above that pivot there, and now you go right bottom to top, right to left. So the next thing you see is this pivot, and you're going to clear above that. In fact, what you also want to do, remember, for reduced echelon is you want those pivots to have value 1. So what he's first going to do is scale row 2 by 1/2. So he took row 2, scale it by 1/2, you get this row 1. So now your pivot is what you want. It's a value of 1, and you can more easily, in fact, clear above as well, right? So once I have that value 1, I take 9 times that row 2, add it to row 1, and you get this, right? You cleared that entry above. So now you're here. You're almost there. You're almost at reduced echelon form. The problem is that the entry is not a 1. So you want to scale row 1 by 1/3 to get you the value of that pivot that you want, right? All these pivots have to have value 1 in reduced echelon form. Okay, so again, you've taken those pivots, you've scaled things so that they're all value 1, you've cleared above, so you're now in reduced echelon form. Okay, and next time we'll talk about why is reduced echelon form so important. It's going to allow us to describe the solution sets to these things, and we'll see you next time.